Thank you very much. Okay. As you can see, my name is Chinwendu Emilian Madubueze. I'm from Department of Mathematics, Joseph Sawantaka University, Makurdi, Nigeria. That is central, north central of Nigeria. So today I'm going to present the work actually I'm doing with my postdoc mentor. So the interest of this work is that I actually wanted to extend the work to apply machine learning to it using a neural network to predict disease. So the interest of Lassa fever virus, because Lassa fever virus is endemic in Nigeria. So that is why the interest of Lassa fever, but it can be applied to any other disease. So, but before then, I have to do a little bit of introduction of what Lassa is. Lassa fever is actually a virus that started in 1969 in North Nigeria, in a town called Lassa in Bauchi State in Nigeria. So the Lassa fever has a rodent, a reservoir, which is form of a rat that carries the virus, but it doesn't kill the rats. So the rats live with the virus all his life, continue to shed it in the environment. It affects up to 300,000 to 500 persons yearly, with 5,000 to 10,000 killed every year. But this number is more than now because most times, because the Lassa fever behaves with other diseases, we cannot actually predict which disease is Lassa fever. For now, there is no approved vaccine for Lassa fever. It's transmitted in so many ways. This is a picture of transmission of Lassa fever virus. This is the rat. It's a particular species of rat. It's not a common rat. It's a rat that most times it stays in a very much dirty environment. Now, because it happens most times in the rural areas where food are spread outside, especially during the dry season, those things can actually attract the rat to the area where people live. Then this virus can be transmitted from the rat to rat, maybe by vertical or horizontal transmission. Then it can also be a spillover to environment where it can affect human beings by shading in the environment, coming in contact with it, and the human can get infected. It can also happen from human to human transmission, which can be in form of blood transmission or fluids between human to human transmission. Most times it happens in the hospital. It has symptoms and signs that behave the same with other diseases like typhoid, malaria, so which became very difficult for you to actually differentiate if actually this disease is a Lassa fever virus. But what happens, especially there is a time that there used to be an epidemic of this disease. What happened during that cases is that whenever there is someone that brought to the hospital, what they do is that they distance quarantine the person while treating the person, because it takes a lot of time for you to identify if the person is actually infected. Now, there is treatment for this disease, but the treatment is given earlier in time for you to prevent it. If it's not given earlier in time, then it will become very difficult to identify. For now in Nigeria, we don't really have a laboratory that is much to identify the disease early. We have a little more, 2 or 3. So most times it takes like 3-4 days for you to actually identify whether somebody is infected. And when someone is infected, if the person dies of the disease, also the dead body can also be very infectious too. So for now, there is no vaccine and the treatment is given early. So now this is what we have in Africa, Lassa fever spread. This is Africa. Now this blue one is Nigeria, telling that Nigeria is mostly also covered with Lassa fever. So more particularly, I'm most interested in Nigeria because that's where it started first. Coming to Nigeria, this is map of Nigeria. We have 36 states in Nigeria with our capital, which is 37. So the red color you see is where the Lassa is already affected and is endemic, meaning that it's almost covering the wide range of Nigeria, as you can see. Now, this graph we have here is the 3 years outbreak of Lassa fever. So you can see it's more like there's a particular period when the disease happens. So those diseases, it happens between November to April, the next year. And that particular time is actually what we call dry season in Nigeria. Then dry season, what happens in typical Nigerian farming is a farming season where people prepare to farm. So in the process, they burn the bush. in the process of burning the bush, there is a tendency that the rats may be running towards the human habitats. So that's why towards that period, anyone identifying being sick, they are always being careful with the person so it cannot spread further. So this is what now motivates me to actually look at Lassa fever virus. So what I'm going to do, I wanted to talk about the dynamics of this disease in a contaminated environment, because studies have it that human-to-human transmission is very rare. So the question now is that how is it being transmitted? And most times when it's transmitted, it's mostly in the rural areas. So we're trying to look at, okay, when an environment is contaminated, maybe the rat is shedding in the environment in the process of eating food. So we'll try to look at how it can be, how the transmission goes. And in doing that, we try to look at the magnitude and time of the peak, because we're looking at, okay, within 6 months. Within these 6 months is from like November to April, when is the endemic, when is the epidemic is high. What parameters affect the transmission? In identifying that, we should be able to know how to, okay, what control can we apply actually to reduce the transmission within this period. Now, within this period, it doesn't mean that other period there is no Lassa. There actually Lassa, but it's not as high as during the period of November to April, the next year of it. Now, I also want to look at it, also the dynamics in two contaminated environments. Two contaminated environments mean that, okay, in-house and outside, because they may also tendency to be there is some rodents inside the house, there are some outside the house. So we want to see which of these environments contribute more to the disease. So this will happen by developing the ordinary differential equations for the two different models. Then we'll carry out sensitivity analysis, also compute the threshold quantity, which is basic reproduction number of the disease. So this is what the model looks like. We have in the human population, because we cannot talk about Lassa if we don't talk about the rodent population too, because they are very important also in the dynamics of the virus. We have the human population, which is susceptible class, people that doesn't have the disease, but they have the tendency to have the disease when they come in contact with someone that is infected. We have exposed class. We have exposed class because Lassa have incubation period for 21 days. So meaning that people you don't get infected and become infected immediately, there is period for you to become infected. Then also we have people that has the disease, but they are not showing symptoms, because in the literature, we have it that 80% of people that is infected are not aware they are infected. They also have symptomatic infected, people that is already aware that they're infected. Also, we have recovery. Now, in this recovery, we have it that people that recover can also become susceptible again, because it has not been established that you recover fully. So that is why we make that assumption. So this, our view here is the virus in the environment, which can be shaded by asymptomatic infected and symptomatic infected human in the environment. Then also we have the rodent population, which is rodents we have here is they are not infected. When they come in contact with lambda, which is a force of infection, they become infected. Of course, they are also shedding it in the environment. This will lead us to the system of equation we have here, ODE, which is given as this. Then, but our lambda is defined in so many ways. The lambda H, which is force of infection for human transmission. A human can be infected by contact between human to human, which can come from asymptomatic infected, symptomatic infected. A human can also come in contact with the rats too, directly with infected rats, because sometimes in some culture, because of bushmeat, people eat bushmeat, and this bushmeat sometimes you may not really identify the particular rats you're having a contact with. So there is a tendency in the hunting or butchering of bushmeat, someone may also come in contact with the virus. Then someone can also come in contact with the virus in the environment if care is not taken by shading. It can be in form of food that is already contaminated with the virus. Now we have spots of infection for the infected rodent, spots of infection for rodents. They can come in contact between both of them. When they come in contact with the rodent that is not infected, come in contact with the one that is infected, that's what I give you the first term here. They can also come in contact with the virus, because in the process of consuming food, they may also consume food that may have been infected by another rodent too. So they can also come in contact with that. So we have the total human population, we have total rodent population. Of course, because it's a system of the ordinary differential equation, we have initial conditions for each of the state variables, which we are given as this. Now, we do a sensitivity analysis of this model. We try to look at those infected compartments. We have the asymptomatic infected, we have systematic infected, we have rodent infected, we have the virus. Now, we did this first simulation. We find out that the rodent parameters are very highly sensitive. They are very, very sensitive. But in order for us, can we actually control the rodents? I don't think it's very, very difficult. They are very tricky that you cannot control, and they also multiply very large. So trying to say, okay, we are going to kill all the rodents in the environment can actually be very difficult to achieve that. Okay? Yeah, you can ask this.
Can you come back to the system of equation? I mean, yeah, this one. Yeah, because you passed a bit quickly.
Okay.
I just wanted to look at this equation. So
SH
means
susceptible people, human being, people that is not yet infected, but when they come in contact with someone, they become infected.
EH is
exposed human, people that is infected but not yet infectious. AI is asymptomatic infected. They are infected but not showing symptoms. IS is people that is infected but showing symptoms. The same thing goes with SR, rodents that is not yet infected, but when they come in contact with infected environments or infected rodent, they become infected. Then IR is infected rodents. Then V is in contaminated environments.
And your target variable is V?
V is contaminated environment. Environment that is already contaminated.
Your target variable in some sense, and all the other one are factors involved in the spread of V.
You say?
I think that V is more or less the target variable. It is the variable you are interested in.
Yes.
And thereafter, you have the explicative variables explaining the spread of V.
Okay.
In different ways. And that's very interesting because it's a causal graph and you have causality inside there. It would be very good.
Okay, thank you. Can I continue? Okay, I can continue. Okay. Okay, thank you. Okay, okay. I even forgot to say the V, because the V has to be with environment. So there is a carrying capacity of environment, which is K. So we do not just leave it like that because you need a carrying capacity for it to be maintained in the environment. So we do a sensitivity analysis in this model and find out that the rodents parameters are very, very sensitive because we are looking at when what we did here is to carry out partial rank correlation coefficients in the system. So those parameters, their value is 0.5 and above, whether it's positive or negative, is very sensitive according to some literatures. So we look at it that the rodent parameter that is within 0.5 and above are very, very sensitive. So we try to say, okay, if we implement control to this, can it actually work? But what kind of control can we implement? Do we say we should kill all the whole rats? Because whatever control you want, for example, there is a rat poison. For instance, in Africa, they used to control rat, but studies have it that they have a tendency of also affecting human beings because children can easily come across that. So we felt that, okay, we are not interested in trying to implement control in the rodent population. So let's fix those parameters. Let's fix them and also carry out a sensitivity analysis in other parameters.
Is it so-called indices? What are exactly these indices?
So this first one here is the clearance of the virus in the environment. This first parameter here,
yeah,
which is very sensitive, meaning that
yeah, I see. Okay. All your parameters.
Yes, all the parameters. Yes, all the parameters. Yes.
Okay.
So this first one is mu v, which has to do with clearance of virus in the environment,
Okay.
which is very sensitive, meaning that if we clean the environment more, the disease will actually reduce in the population. That's what it means, because it's a negative. So increasing it will actually going to reduce the body of the disease. Now, also we have this one here has to do with rodent-to-rodent interaction, transmission rates. So meaning that if the more the rodents are coming in contact with each other, the more the virus remain in the environment. So we find out that, okay, this is also the rodent death due to death rate for rodents. So meaning that it's also it's very, very sensitive too. So we say, okay, because those parameters, rodent parameters are very sensitive, we want to fix them and still carry out the sensitivity analysis on this. But this is magnitude, peak magnitude, the parameter that contribute to the peak magnitude within that period. Well, also, the same thing goes with the peak time. What are those parameters also contribute that? Also find out some of the rodent parameters also contribute. This is the transmission between the rat-to-rat transmission. Then, of course, this is the mu view, which has to do with the more you have a clean environment, in order to take away the virus, the more. So it will also increase the time peak, but it will reduce the magnitude of the peak. So when we fix that, then we have this result here. So we now see that one, this is, of course, the mu view, which is like clean environment, will still be very sensitive. Now for the magnitude, but then we have here that recovery rate of this asymptomatic infected is very sensitive, meaning that the more people that is asymptomatic infected they are recovering, the more the disease will actually reduce the environment. And this is true because they are not aware they are infected, meaning that they are very dangerous in the environment. So the more people can be identified who are asymptomatic, the more the disease will actually reduce in the environment. So we also have it that human to virus transmission is also very sensitive too, which is also high here. So meaning that because if, of course, if someone is not informed about the food and everything, because this is not human-to-human transmission. We have a situation where somebody is infected and live in a house with someone throughout the period of the virus, the person did not get infected, meaning that the human-to-human transmission actually happened in the hospital when there is actually the transmission of blood or there is exposure of blood, but for within the human contact is very, very difficult. So the question now open is that what is it that is actually causing Lassa? So that is why we are looking at environment, and environment plays a lot to it, because when it comes to African setting, during the dry season, that is when the farmers dry their food outside. So that time is also exposed a lot of things that can attract the rats. And also that is the period when the bush are born, and rats is also finding their ways where they can searching for food too. So we now see that these parameters are very, very, they are key factor for transmission rates. The rodent shedding rate is also very important there. The virus decay rate is very important there. Then the recovery rate for asymptomatic infected is also a key factor to look at when we want to also try to reduce the peak magnitude of their virus. Now, when we look at the peak time, the parameters that is very sensitive, we can see a virus decay rate. Human to environment transmission are very, very sensitive in that too. Why others do not show a significant result, because we are looking at those that has a partial rank correlation being from 0.5 and above. So after this, so yeah.
Say something about how you're measuring sensitivity. So I'm not sure I'm familiar with PRCC.
Okay, from the what I read that being a parameter is sensitive if the PRCC is 0.5 and above, whether positive or negative.
And what is PRCC?
Okay, PRCC is partial rank correlation coefficient. So what I use here is Latin Himbakov's scheme.
Yeah.
Yeah. So that's what I running a 1,000 runs.
But how do you estimate these parameters?
Okay, for these parameters, estimating the parameters for now, I did not make use of estimating I estimate the parameter using literatures where they are estimated the parameters.
So these parameters are known?
Some of them are known, yes. Yeah, some of them are known. Yeah, some of them are known.
Okay, it is ground truth. And okay, and in your numerical results part, you will estimate these parameters and compare them to the ground truth.
like what the numerical simulation I did here is that these parameters, some of them, like for example, some of them are based in the literature,
Yeah.
extracted from literature. Then, and I create some of these parameters, a uniform distribution for them, trying to use apply the Latin LHS Latin Hypercomb scheme in order to calculate the partial rank correlation coefficients of each of these parameters in the model. Yes. So I have to run a 1,000 runs of each of them. So it has a range. So the range selected, some of them are 0.8 of this parameter as parameter values. Some of them are 0.08. So it depends. So within that range, it will run a 1,000 simulation of each of them.
Okay.
Yeah.
So you have a Bayesian approach to estimate the parameters?
Say?
You have a Bayesian approach to estimate?
No, for this particular work now, I did not estimate the parameter from the data.
Okay,
No.
okay.
Yeah. So because of what we have here, so this is for one environment where the virus is just one, all the environment is just one environment. So we now look at when it's two environments. Now we are looking at there's in-house environment, there's outside environment. So now we are divided the environment into two. We have V, we have W. Each of them also shading into the environment. We now carry, this will give us a system of equation here. Because the system of equation here is a closed population for human population, but for the rodents is an open population because within 6 months, rodents can have more new babies, more offspring. So for the human population is a closed population. So we have our system of equation from that flow diagram as this. Now for the force of infection, our force of infection will now extended where the human can come in contact with the in-house virus. It can also come in contact with outside house virus. The same thing goes with the rodents too. We have it as this. Now we run a simulation. For this simulation too, also the rodent parameter, they are all fixed. We do not vary them in part of the, in the sense that they are fixed is that we do not factor them into the looking at how sensitive they are. We just fix their values. Yes, while the others are taken care of. That's what we did here. So we now find that human recovery rate, transmission rates, the virus decay rate for human are very, very sensitive. The same thing with the shedding rate too, contaminated rate for they are all very sensitive for when it comes to the big magnitude too. So this is what we have here. The same thing go with the peak time. The peak time is not the same thing happen, but not really for all of them. But one thing you notice that most parameters are very sensitive when it comes to human population. There are more parameters being sensitive when it comes to human population. And also we see that for the both population, we see for the V, there we have a sensitive parameters, which we have as this. So we have a VH and VW. So the transmission to both environments are very sensitive. So this is like extension of what we have in when it's one environment. When it's two environment, the transmission to the environments, both of them are very, very sensitive. So what's happening here is that is a result that we have gotten so far. And one of the limitations we have in this result is that we do not actually fit it to the data. Because when it comes to the data of Lassa, the cases are just like how many people are infected, weekly cases, how many suspected cases, how many people are confirmed cases, how many people that died. So meaning that we cannot get the environment that is contaminated, the number that has to contribute that. So those are some of the limitations we have in this work.
You don't have data at the moment?
Yeah?
You don't have
yeah. So far, this is what I have. No, you can ask me questions. I'm open for questions.
So it's mostly the variable linked with the environment, which has, you say we have the number of persons who are here, but you have not all the detailed parameters.
Yes. We have the number of cases. Every week in Nigeria, cases are reported that is infected. Every week in Nigeria, cases are reported that is infected. And those cases are categorized in suspected cases, confirmed cases, death confirmed cases. Those are the way the cases are confirmed. So there's no like how many people touch the contaminated environment or something like that.
Okay.
So that is the kind of data we have. So that is the and that is the kind of data also I have that I want to see how is possible to apply neural network to it. What can I do to it? How can I apply machine learning to such data? So that is the problem I have to be here to see how I can solve that, because coming from the modeling aspect of analysis and everything, I'm looking forward. I'm almost done with the presentation. Okay, before then, this distribution we have, we'll try to plot the histogram of those distributions. How does the histogram of those distributions behave? For this first one, we have this is a asymptomatic infected, systematic infected, rat infected, and outside the environment and inside the environment. Now we see for the human population, we see that there are more of the screen to the right. But while for the rats, it's more of like evenly distributed, but now actually as if it's a normal distributed too. Then for the environment, we have it more screen to the left. So this is to show what this histogram is more like. Within that 1,000 runs, each of those parameters will always produce infected people. Each of the parameter range within 1,000 produce number of cases. So within that 1,000, we plot their histogram to see how those distribution, their counts behave. So we see for the human population, the counts screen to the right, while the environment screen to the right, then the rat is evenly distributed. So this is what we have so far. Then we'll try also plot the solution. Of course, all this is have to do with system of ODE. So this is the way the solution behaves. The solution of that system of ODE. We see that the exposed class, there's actually a peak. Then we'll plot it within 200 days because we are looking at within 6 months of the dry season. These are symptomatic infected. This is symptomatic infected. This is recovery rate. Now this is for the rats, susceptible rats. Then this is infected, the virus. So we can see that this is actually more like endemic, but we don't know how long it will take. We can, even if we extend the days to more time, after that particular period, Lassa is not eliminated finally, but it's still very, very small in the environment. So this is what we have. We notice after 100 days, before we can now see that it is declined, but it still remains in the population. So for now, this is what I have been doing. Even apart from this, I also have some work also doing optimal control of Lassa fever virus, also trying to look at cost effectiveness of those control, which I also have done. But in the meantime, what I actually want to look at now is that application of machine learning to Lassa fever transmission in order to forecasting using a neural network approach. I also want to looking at stochastic modeling of spread of Lassa fever virus, which also I started when I was in Oxford 2 months ago, but I've not concluded it. So I'm trying to look at those aspects. Thank you very much. Okay.
You showed your the distribution of the different outcomes over the different runs. I missed what was changing between the runs. Was there some randomness you were introducing?
No. I was not introducing this some randoms. It's just from the distribution, from the counting, from this sensitivity analysis. I tried to plot the distribution of those counting coming from each of the runs. For example, for each of the 1,000 runs, like the range of the parameters will pick, like for example, beta will pick a value from the 1 runs. Then each of the parameters will also choose a value from that. They will now have each of the state variables. The same thing goes to 1,000. Then at the end of the day, I want to see those counts. How did their distribution, how does it behave? What kind of distribution do they have? That is what I did not introduce anything.
So each run was one of the points in your parameter space that you sampled to do your sensitivity analysis.
You said?
So each of those runs was one of the points in parameter space.
Yes.
The model.
Yeah.
No, that's
yeah.
I see.
In terms of model fitting, you said you haven't got the data for the environment, but you have got the data for known infections.
Yes, I have a data for infected cases,
Yeah.
confirmed infected cases, suspected infected cases, then deaths, confirmed infected cases. That's the parameters I have.
Okay. But so
And it's a weekly parameter.
cool. Okay. So that to some degree correlates to your infected people who are showing symptoms, your infected people who might not be, and there is a death output. So you could potentially do something like a Bayesian calibration to those outputs, which would give you a distribution, probably a non-unique distribution over your possible parameter values, and you could feed that distribution of parameter values into the model to give you a distribution over, like suspected distribution over the environmental
Okay.
stuff.
Okay.
That was my first question. You have some information, but not all of it.
Okay.
You could maybe.
Yeah, yeah,
Estimation of hidden.
Yeah, sorry. Yeah. Essentially, yeah.
Okay. Okay.
Which is we're not quite doing all that stuff, but that would be like a potential application of statistical analysis for the model as you put it.
Okay. Okay.
And
That would be nice. Yeah.
And another idea is that you have a causal graph, and in your causal graph, you have so unknown variables, which are some noise in some sense, which is
Yeah. Yeah.
unknown
Yeah.
variables, and you have observed variables. So maybe you can perform, try to see, to estimate the sensitivity analysis index. There are papers about causally aware sensitivity analysis. And then you can use this framework. Maybe in your case, I can send you the paper.
Okay. Yeah. That would be very.
They,
That would.
they could be very interesting things to do. And thereafter you can use, as you said, you can use the data you have, and it could really complement that you have done. I'm sorry, it's non-neural network.
No, but it's good. Yeah, because I'm also very much interested to look at another aspect of it. Yeah.
Neural network is also interesting.
Thank you very much. So.
Just to follow up on this proposal, which, best of my understanding, makes a lot of sense. The question of the prior is quite important. So here
Yeah.
you said you use uniform. How did you choose the balance for your uniform distribution on the parameters? What was driving the choice?
Okay. Will I even? I don't know whether I remember now.
So there is a lot of work on insulation, so define files that are kind of
Okay. Yeah.
some file knowledge. So basically, one aspect is to define files, another aspect is to condition on your available observation of the calibrated model to kind of first define a collection of file distributions or join file on your parameters, and then to condition on the available data to get a Gaussian distribution of the models,
Yeah.
which is already informing you in some sense. Then you can also sample from this and get some more informed histograms.
Okay.
And maybe then you can also try to contribute that to guide further data acquisition strategies and reducing some things. So then there is a whole framework that basically
Okay.
involves a number of choices.
Okay. Okay.
And especially to continue on that, if you show again your causal graph, maybe the case, I mean, all these variables you talk about are of course meaningful, but maybe the case that if you want to have some identifiability from your data, because you have these hidden variables, maybe it could be interesting to do some model reduction, through, of course, the causal approach, so that in fact you succeed in making a good prediction, but maybe some of your hidden variables, even if they are key, won't be able to estimate them. So it's really
Yeah. Okay.
If we can to add that there's been a lot of literature development in the last few years, especially following the COVID-19 episodes, on SIR,
Yeah, yeah,
SIRS
yeah.
models, and also Bayesian approaches to all of those models. So these are basically compartmental models.
Yeah.
And yeah, there is you probably find a couple of entry points in the literature to kind of
Yeah, yes, I like it.
move forward with these interesting data sets that you have.
Excellent. Thank you very much. It was a great talk and
Thank you.